We can just say hi and welcome to everyone for this session on the workshop on digital twin and design at this conference. I hope you can all see the slide set now being shared as well. I think we'll have a quite exciting session here, and I would just like to introduce myself briefly, followed by co-organizers, and then we can get going. So I'm Ola Isaksson. I'm in this context, I'm a professor in product development at Chalmers University in Sweden. And in this context, I'm also co-chair in the Design Practice SIG, which is one of the organizers here, together with Oskar Nespoli, who is also on the meeting. And I would like to hand over to Professor Eckhard Kirchner to present himself as well.
Ola, thanks for the kind introduction. Eckhard Kirchner. I'm heading the Institute for Product Development and Machine Elements in Darmstadt. Potentially, some of you know my predecessor, Herbert Birkhofer. I'm having the honor to further develop the heritage of him and also Gerhard Pahl. Now we're trying to somehow move over to the more and more digital world, and the topic of the digital twin has turned out to be of particular interest. We had a discussion in the Design Practice SIG, as Ola mentioned. Oskar Nespoli was one of the main drivers. I think he will not claim to be a co-organizer, but indeed he spent a lot of time in the prep meetings, and I just didn't want him to pass by completely unnoticed. So Oskar, thanks again for your help and for your comments in the preparation. And I have to also acknowledge Yannick Koch, who did the most legwork in the preparation of this workshop. And Yannick, if you want to continue before we go into the outline of the this workshop.
Yes, thank you for the introduction. I have just some short words on using Hopin. We are limited to 20 persons who could share their voices and their video. So we have to take care of these, and we also reglement it. And in the next steps, I think, Eckhard, you will tell us about the processing of the workshop. I will go to the agenda.
Yeah. Exactly. Here we have the agenda. Idea is, after this brief introduction of the organizing team, to have a series of inspirational talks, each allocated around about 7 to 8 minutes. I would like to encourage all of you to take down notes that we discuss about any questions in a dedicated Q&A session after the last inspirational presentation. Round about 1 hour for the presentations. Then it was taken. We have 6 presentations, each 7 to 8 minutes, as mentioned. We have this discussion afterwards. Then we go into group work on selected questions. We will report back to the auditory and wrap up round about by 16:30 European time. That's the plan for the next couple of hours. Did I forget anything? Yannick, Ola, do you want to add comments? But I think this was...
We can possibly say
sorry.
one more thing, and that's
Ola, you're going on and off constantly.
Skip that then.
Maybe then just some more words from my side. We are going to work in Miro, and we prepared some boards, especially for the group work where we can all work together. I will just shortly show you the board. We will share this with you. So the first, we have some questions where you can answer these and to get a view about the digital twins from your side, especially on what is the definition of a digital twins from your point of view, and also examples on how to use the digital twin. It's also combined with the presentations given by the speakers in the following, which will also elaborate on these themes. On this next page, we have visiting cards, where you can create your own one, and in the following, you can use these to get in contact and also show where you want to participate in the future. There we have some short networking, and also we have different slides for the group work, where we will assign some topics where you can work on, and in the end we will, as already said, wrap all things together and look how we will proceed in the future.
Yannick, could you please distribute the link in the chat?
I think the plan was to do that as soon as we have completed the presentation.
Okay.
But we could also start that beforehand to allow you also to take down your questions during the presentations. I think that could be a way of avoiding that we lose any kind of feedback.
Now, my only idea was to test the login on the Miro board during the presentations.
Yes, for questions, you can use the chat in Hopin and also the Miro board. So, is there anything else from your side, Ola? It seems like your microphone is still not working.
Yeah, it's always going on and off.
Okay. So then I think we could start with the first presentation. We are now going to Philip Abele from SEW, German, mainly gear producer, and he will talk about the digitalization of the manufacturing process mainly. And Philip, the stage is yours.
Thank you, Yannick, for the kindly introduction, and thank you all to talk here. And it sounds challenging because inspiration talk is definitely a new category I am talking. So hopefully I fulfill your requirements, and I just start with sharing my screen. And it would be great if I could get a short feedback if you see my slides.
Yes, we can see them.
Okay, so I started my stopwatch that we keep the pace, and yes, I dive direct into the topic. The topic about my talk is DriveHub. It's our framework, our platform for development and operation of our modular gear unit systems. And I will focus on the part of design automation because it's the beginning of our digital journey of our twins, and also from the connection to the design conference, I thought it would be a good connection to start with the way how we automated design. Yes, and for each section of our framework, we follow a certain pattern. The pattern is as following. We have 3 types of roles. We have a developer of the system, then we have knowledge engineers, so that are people who are modeling classes or domains. whether you are more familiar with software or you're more familiar with design. But I would say classes and domains from a business perspective could be compared. Yes, and then last but not least, there is the third kind of persons, the designer. They enter they label the data. So how is our system designed? The main idea is we have two types of input data. We have data in tabular form, and we have data based on CAD parts. And what is the result of our design automation? We fully autonomously produce assemblies, parts, and drawings for our further processing in simulation or manufacturing. So the system is based on an event-driven architecture, mainly powered through Apache Kafka. And the idea is that we have a Kafka, a message broker in our system who receives requests from producers to produce parts or drawings from our modular gear unit system. And the consumers are dedicated workers in our cloud computing network who will actually produce the requested data. And we do it for scalability and for availability, this divide and conquer concept. So a short overview of how a certain design could actually look like. On the left-hand side, you see the user who is interacting with the platform, and the user interacts with the one hand side with databases and tables, and on the other side with parts, mainly in our PLM system, we're working with SolidWorks. Therefore, this is this red cube down. Yeah, and then there are some details about how we implemented it using RESTful services and microservice architecture to fulfill our cloud native requirements. Yes, and how is the second part? The second part is the knowledge engineering. Knowledge engineering is the part how to model the data to be fully automated produced. So we have on the one hand side designed a certain pattern based on parts and master data and connected them through the different stages of manufacturing, starting from a turn part, going to a semi-finished part, and finally ending up in a finished part 1 and a finished part 2. And here you see, for simplification reasons, just the drawing of a planetary gear wheel we are producing. Giving you just a few numbers, we have 40 parts in the turn part section and 80 parts in the finished part section, and we're producing these parts in 14 up to 20 seconds. And this gives us an agile way of doing lots of loops during our design circles. Due to the processing time of SolidWorks, the times to producing drawings are a little bit longer, but the fact getting the data takes longer than producing the drawings itself. Yes, and fulfilling the sketch, it's necessary also to connect the drawings and the master data with the instances. Yes, and how does a system look like? We are following an item ID concept. So we modeled, we given the system certain sections and divided it that it is possible for several people to work parallel in a distributed way on the same data set. Yes, and also set up a use case for an assembly manufacturing, and we also set it up in in the same manner like for the drawings and for the parts. We have some master files and we have some master data in our database, and then we have some workers in our cloud system who are combining these parts to producing fully digital assembled gearboxes for further processing for simulation or other topics. Yes, and last but not least, there is the task which also has to be done. Label the data. On the left-hand side, you just see exemplary entries in the tables we created in our database. And that is definitely one of the challenging tasks of all. Yes, foster the people to have an easy but also a safe way to interact with the data of the database. Yes, and that was it. A rush through our Drive Hub framework in 7 minutes, 20 seconds. And feel free to contact me and get ideas how we work with this automated data in later stages like calculation, simulation, or also in engineering or variant configuration. Yes, thank you.
Thank you very much for that first inspirational presentation. I started to yet take the first notes myself. If there are no emergency questions to Philip, I would propose that we continue with the second presentation. I got the note here that Eckhard Söderberg is going to give the second presentation due to the fact that he's also having to manage a couple of different meetings. Eckhard, are you on? I can't see you.
I think it's Christina Wernfurt who
okay.
holds the presentation.
Christina,
sorry, that was my fault.
Sorry for that. Yeah, the stage is yours. If you want to share your presentation, we're happy to listen your
thank you.
The digital twin.
It seems like I lost this share button. It used to be there, but it's not anymore.
The share button is right below our videos. It's the display which is crossed with a red line.
Yeah. I needed to leave the full screen. So let's see.
Meanwhile, we can say that Christina is also a professor on the same group, together with Eckhard, on geometry and robust design at Chalmers.
So am I sharing the right presentation? No, obviously not.
Your presentation outline, but not the presentation stream.
It's the wrong. No. Yeah, that's better.
Yeah.
Okay, so thank you. Yeah, so I will present this inspection data needed to support the digital twin for geometry assurance. So I am a colleague of Ola at Chalmers, and my research area is mainly focused towards geometry assurance, tolerance management, dimensional control, whatever you choose to call it. But my idea was to start with saying something about digital twin, how I see it. And I like this definition of Kritzinger et al., where you have this, I guess you're familiar with this, but the main thing here is that in order to have a digital twin, you need to have this bidirectional data exchange. So you measure or get some information from the process or product or service that you want to have a digital twin of. You analyze that and you come up with some kind of adjustment or feedback that you bring back to the process. So we start with that and try to apply it to this research area, which is about geometry assurance and geometrical variation. And the problem that we are dealing with in this area is that we have geometrical variation on parts. So due to the manufacturing processes, they vary in form and in size. We have assembly variation, joining process variation, and that might lead us to products that do not fill the assembly requirements, so they do not fit together, or it can be functional or aesthetical requirements that are not fulfilled on product level. So we need to deal with that. And we have a lot of different tools to do this, but if we focus on one of the main parts, which is called variation simulation. And the idea with this is that if we look to the right on this slide here, you see that in early product realization phases, we create a digital twin, and that is a simulation model, more or less. So we build a simulation model aiming to predict variation, geometrical variation on assembly level or product level, and the input is part tolerances or part inspection data together with information about the assembly process and the part geometries, of course, and so on. So this is done at many manufacturing or larger OEMs and manufacturing companies. They do this kind of simulations to predict what variation you will have given certain tolerances, certain concepts, and so on. So we start with this. But if we have the simulation model during the production where we have inspection data, let's say that we scan all the parts on part level, we can use that to feed our simulation model, and then we have a digital twin, because we can use this information to optimize the joining process, for example. So we can suggest that, okay, based on those parts that we have scanned data of, how should we adjust the joining process? So we can match different parts, that what we call selective assembly, that this part goes well with this part. We can do small changes of the locators in the fixtures, or we can change the sequence in which we, for example, spot weld the parts together. That, okay, now we choose this sequence or this sequence, which is the best one for this assembly. So then we have a digital twin. And this is so far mostly on research level, so to say, but we have shown that there is a lot of potential in this, so we can actually reduce the geometrical variation on assembly level with up to 60% compared to not doing those adjustments. So a lot of potential using a digital twin like this. But the thing that I wanted to raise here in this context is that we need, of course, to feed digital twin with the right data. And I think that goes for all different application areas, that it's very important what kind of data we use as input to our digital twins. And no matter what accuracy we have in our simulation models, if we do not have a good input, then it's not so very useful. So, of course, we need to have the right kind of data. So in our cases, we need to measure the right parts. We need to keep track of the parts and so on. We need to be aware of inspection accuracy. So we have good measurement equipment. We need to think about how to inspect things. For example, I have some picture here showing a quite complex fixture. And when talking about sheet metal parts like I do here, it's quite common to put them in a fixture and we apply a lot of clamps. But then we actually deform the part, so we measure more kind of the shape of the fixture than the shape of the actual part. And that makes the data not very useful for those kind of simulations where we want to predict spring back and so on. So instead we should measure it in a non-over-constrained way. And we are actually working together with Volvo Cars on this to use some much more simpler equipment during inspection instead of those complex fixtures. Also, when to inspect, if we have long simulation times, maybe we need to inspect at the supplier and not inline inspection can be discussed, of course. Also, some kind of confidence in data. I mean, if we measure like the fixture repeatability, we need to have enough data to base those estimations on. So those are some kind of open questions, and I think that we should have some kind of indicator of the quality of the input data for a digital twin. How good must the data be to be useful is another question. So I think I end the presentation with those open questions. Maybe it can be discussed later on during the workshop. So thank you very much.
Okay. Thanks, Christina. I take the initiative. Very detailed presentation. Thanks for that. Again, any immediate questions to Christina? If that's not the case, we should stay more or less in Sweden and having Freddy Fuchsin from Volvo reporting from his perspective on the digital twin with his inspirational thoughts. Freddy, the stage is yours. I'm curious to listen to you.
Thank you. You hear me well?
Yeah.
Good. And then we try to share also, see if that is working as well. Do you see my screen?
Not yet, at my end at least.
No.
While,
Me neither.
me neither. While starting up, we can just let you know that Dr. Freddy Fuchsin has worked
Hold
for...
on, no problem. Now you ought to see my screen, right?
Yes.
Good. Okay. So my name is Freddy Fuchsin. I'm working at Volvo Group Trucks Technology inside an organization called CAST, Common Architecture Shared Technology. And what I will present today is some of the challenges that we have been encountered and are facing going forward when it comes to geometrical documentation complexity, because that's something that is a true challenge for us. Brief background, started off in '96 at Volvo, conducted my PhD between '98 and 2005 within the area of geometrical configuration management. Today, still working in that area, but also in assortment analytics and vehicle performance. My and our perspective on the digital twin immediately brings in the product lifecycle dimension to it. And what is imperative for us is the initial area of the product lifecycle when we are talking about the creation process. And digital twins are so many different things. And what I will put my focus on today is the geometrical representations, because if we have those and we have them quality assured, there is a huge potential for leveraging that information throughout the extended enterprise. So that's the key that we are targeting right now. But the thing is that on top of the creation side, which holds a lot of challenges, and I will come back to that a little bit later, we also have the other side of it, and that is really when we have left what is traditionally referred to as development, and actually are having products out to our customers where we would like to leverage again on the digital twin and the potentials that resides inside that setup. And there we enter into other aspects that we need to take into consideration that is not perhaps appearing inside the creation phase. And then, of course, we must also have the complete setup where we also take into consideration the retirement of our product. And this is really the entire chain that we are trying to hold together. And this is a long time perspective on this. There is a challenge for us, and it is briefly illustrated throughout this picture. We are a company today with multiple brands, and we are at the same time a global player working with trucks all over the world, so emissions and all of those different things, and more lately also then, of course, zero emission vehicles, which comes into play, where we are launching this year. But on top of that, things that we tend not to take into account immediately, but is a necessity for us, is the legislation part of things, because legislation requires that we adapt the vehicles to the customers and so forth. So there is a number of different challenges that we must balance, and the consequence of that is really that we will have a standard offering that is tremendously huge and contains so many product combinations. And that is a true challenge for us. In the creation setup, where we have spent enormous amounts of time, this is really what we want to achieve. This is a truck that is based on a customer specification, automatically generated, and it should be as accurately as possible. But at the same time, we must have a balance here, because this is one of the topics that I want to bring in here is really, okay, we could potentially create the truck 100% accurately, but that would also implicate that we need to spend those resources. And do we have a good business case on that? When we come to a situation that we have millions and millions of combinations that we need to position correctly and model correctly, it becomes a little bit challenging. And that's really what we are facing today. So in this area of creation, we are having spent a lot of time in the area of product structure, how we build up our PDM systems, but also in the area of how we actually create the geometry and which practices and methods that we need to take into account. We have also adopted philosophy where we are distinguishing between physical bill of materials and digital bill of materials. And that also implicates that we need to take in the bridging dimension to this, the bridging between the digital bill of material and the physical bill of material. Another thing that is challenging is, of course, different phases, early phases versus later phases and so forth inside the creation setup. And then on top of that, we are not only selling the truck is also utilized at, for example, the bodybuilders or in CA, custom adaptation activities, which is a true challenge because then they're actually modifying our digital twin. So when it comes to the consumption area, we must bring those dimensions in from sometimes external partners in order to have a true digital twin. And that is one of the challenges with the consumption phase, which is really the long phase in the product life cycle, because it lasts at least somewhere between 7 to 12 years normally for a truck. And in this setup, when we want to communicate these type of things, we also have, of course, a challenge when it comes to storage solutions and solutions for combining and collaborating with different types of stakeholders. And that naturally involves aftermarket, manufacturing, and so forth. Another thing that we are working a lot on is, of course, different types of lightweight formats for different purposes and also neutral formats. And another challenge is, of course, the digital twins continuous update throughout the product lifecycle. And retire, I don't think I need to go too much into that one, but that requires a lot of additional information about what the truck is really composed of in order to perform it in a thorough manner. 8 minutes, roughly. Thank you for your attention.
Thanks for that interesting presentation. Ola, do you want to introduce Ben Hicks?
Yes, please. Can you hear me now?
Yeah, it's much better.
Okay, thanks. Sorry about the trouble. So next speaker up is Professor Ben Hicks from UK in Bristol. I can see you online. You're more than welcome. You have also been quite active in the field of digital twins, and I think you will share some of your experiences from that. You're more than welcome.
Thank you very much, everyone. And can you hear me? Good. So I shall share my screen. Do you see my screen now? Yes.
Yes.
Excellent. So thank you very much for the invitation to present an inspirational talk. And my talk today is consistent with Christina's definitions, which is good. it's always a relief. But my talk today is around, can you see the twin amongst the sea of digital virtual models? And certainly one of the biggest challenges, I think, for the community, for industry, and for us as researchers is what we call conceptual stretching and conflation of what a digital twin actually is. And so I like to use the Where's Wally or Where's Waldo backdrop here, because if you're familiar with that, you have to spot or find Where's Wally or Waldo in amongst a sea of ostensibly very similar looking individuals. And what I'm going to talk about today is I've got sort of 7 slides. A lot of what I'm going to talk about now is being drawn from quite a number of events. So from participating in a number of ISO committees and a recent study in the UK by our Government Office of Science, who really wanted to understand what is a digital twin and what are the research challenges around digital twins, and essentially where should the UK Government Office of Science and BAYES be investing their money. So I'm hoping this will advance. So most of you will be quite familiar, I hope, with the history of digital twins. This is often overlooked by many, but early 2000, John Vickers of NASA. NASA had this driver. Previously, they kept a physical copy of every artifact or asset they had in space. Downsides to doing that is costly, etc. So they pursued or started to investigate the concept of a digital twin, so they could keep a digital virtual asset or model of all their assets in space that was continually updated, so represented the current condition of that asset. Those sorts of techniques were built upon and I suppose applied in the aerospace sector in particular, where they had a lot of existing tool sets around condition monitoring to sort of take those to another level, whereby you started to have this closed loop. So companies like Rolls-Royce, really world leaders now in digital, often highlighted as one of the world leaders in digital twin technology, certainly for gas turbines. About 2014, the sort of paradigm of digital twins was applied or has been applied to production systems quite effectively. An area we as a research group we did a lot of work in. You have your SCADA systems on your factory floor, so you've already got a lot of sensing and instrumentation, and it was about then integrating that with the models, sort of discrete event simulation type, such as AnyLogic or Witness. So you can actually almost close that loop and do real-time simulation and feedback and squeeze out a little bit more efficiency or greater productivity for the production environment or production system. Around 2016-17, we started to see digital twins being applied to infrastructure, and the idea there really was to start to close the gap between what happens in reality and the models themselves, to improve the models, so things like substructuring and structural dynamics of those buildings or assets, to try and close the loop and understand why the models were over or underestimating, and to refine and improve those models. And then 2018 on, we've seen quite a bit of research across the world where engineers or engineering design researchers are starting to ask the questions, what could a digital twin offer during the early stages of the engineering design process? So Freddie alluded to that sort of creation phase. What can a digital twin offer value, and how can those assets be used ultimately to create a digital twin, perhaps through life cycle? So the definition here, which Christina covered, that quite commonly we see this sort of model here, where we have a physical system, some data is captured, and that feeds into the digital models, and then there might be a user or an engineer who looks at the results of the digital models. Fundamentally, that's not a digital twin. That is, just as Christina highlighted, that's a digital shadow. The digital twin has an extra element, and it has the 4 elements: the physical system, we have the real, and I've noticed I've changed to real time, where that depends on the application really, but real time capture of data. That then is fed into or used in the digital models, and then that is in some form of closed loop that's used to interact or control the physical system. So that is a digital twin, and that's a really important differentiation. And that difference made its way into our UK Government Office of Science definition and quite a number of ISO standards now. And that's really highlighting that the digital twin is a collection of one or more computational representations. So people, and increasingly we talk around a digital twin system. There's a flow of real-time data, where real-time depends obviously on the context and the application. But importantly, that other aspect is it's that remote interaction or control with the physical asset. So it's that closed loop. So what we can do then, and certainly in the UK, we've had a number of workshops, I think not dissimilar to this workshop, starting to unpack the digital twin and say, well, where's the new research? What are the research challenges? And one way of doing that is to look at these 4 interfaces, so we can have a slightly closer look at those interfaces. And if we start with the physical system, we've got to measure and monitor that physical system. So there's a metrology and sensing interface if you want to generate that data. Then once we've got the data, we have to manipulate that data or incorporate that into our digital model. So there's some conditioning and combining that needs to take place. And then we've got, from the digital model, if we're going to interact control, we have to generate some understanding or insights from those digital models, that collection of models. So there's a learning and decision-making element to that. And the final bit there is about automation and control. How do we actually interact or control the physical system? And we can look at that in a little bit more detail. And these are some of the, I'm sure some of you now will see these challenges and think, yes, there are aspects that you have had to deal with or in your research, or you'll be aware of research that's focusing on these. And again, if we start down with the metrology and sensing, IoT, sensors, comms, metrology, contact, non-contact, they're all enabling technologies for that metrology and sensing. If we look at conditioning and combining the data, data fusion techniques, how do we filter the noise? Signal processing techniques to look at feature extraction, really important. How do we, identify and extract those patterns? And terms like big data. And again, they're enabling technologies, but are established research areas in their own right. If we look at learning and decision making, we see certainly in the UK, lots of projects which are digital twin centered, but talk about surrogate models, machine learning, AI, design of experiments, digital threads, optimization. Again, established research fields, are quite mature in many cases, things like optimization, 30 plus years established. If we look at automation and control, actuation technologies, techniques, control algorithms, robotics, soft robotics, distributed self-powered, intelligence and autonomy, all research areas and disciplines that some of us and our colleagues will be very active in. So it sort of begs the question, and it's one of the tensions of, do those areas represent challenges for digital twins? Or are they established research areas in their own right? And if they're established research areas in their own right, that sort of argumentation leads on to, well, what are the research? Where's the research in digital twins? And in order to explore that, where we've ended, is to look at the whole. So you've got to really step back from it. And ultimately, what the digital twin is, and the digital twin system, it is a learning loop. It enables us to learn and to effect some sort of control over the physical system. So you're almost automating the learning loop. And if we automate the learning loop, we can start to take an engineering approach and say, okay, well, what are the requirements? What's the purpose of this loop? We can then say, what insights are needed and when? So what knowledge and understanding needs to be generated, handled by this loop? And again, Christina talked about the data and data quality. What needs to be handled? And what confidence or precision do we actually need, whether it's a flood defense system or whether it's a building control system or the city and transport? What confidence or precision do we actually need? And then what data and when? We can look at what models are needed, what fidelity of models do we require? How is feedback to be implemented? And lastly, and really importantly, how do we evaluate cost benefit in this context? Does the application require a digital twin? And what I'm going to do now is just give you a couple of examples where digital twins offer compelling value, but equally there are many examples out there where a digital twin and the concept or paradigm of digital twin may not offer any value add at all. Actually, the cost of creating and maintaining almost dwarfs the benefit or value of having a digital twin. So the key thing here is for the digital twin, it's about the whole. It's a learning loop, and understanding the requirements of that and the purpose drive everything else, which are then become secondary challenges that need to be addressed in order to deliver or realize a digital twin that offers value. Very quickly, because I'm conscious of time, I've picked some examples that you can all go and have a look at. This is an example of Autodesk where they used what we call a product digital twin, instrumented a chassis with hundreds of sensors, collected data, redesigned the chassis, and iterated around that until they built the vehicle, which was raced by the Bandita brothers. A good example of performance twin, very, it's worth those not familiar with it. It's definitely worth looking at the latest papers and white papers published by Rolls-Royce, because their digital twin technology, it's two-way now. It's not just sensing things and reporting back. It's actually the control center can request specific information from engines in specific formats, and actually request that and assimilate that. And importantly, what they're doing is looking at the context. They're looking at and understanding engines, different parts of their flight path, different conditions, whether that be an ash cloud or similar, on different routes. And they're then looking at that contextual information and then optimizing and refining and optimizing their engine performance for those particular contexts or routes. So they're learning and transferring learning dynamically as they go, with about 14,000 engines currently being monitored. Then the third one, which we often talk about, is a production twin. And certainly as a group, we do quite a lot on this, where we're looking at that, the whole system, the manufacturing system, and then sort of machine tool level. And we are modeling the whole system or factory floor, and looking at, whether it's a GKN, etc., looking at how in real time we can modify, change the assembly process, for example, such that we achieve overall compliance. And these can be to drive, it's process optimization, quality management, etc. So those are three quite generic examples where digital twins offer value. So then it begs the question, and we go, when and why do we twin if twins aren't for everyone? And there are a number of touch points from other meetings that I've had, really where the system is very dynamic. So its condition, behavior, inputs, environment, and are changing, or very difficult to predict. So things like flood defense systems are a good example in the UK. Most of our utilities or water authorities have been using digital twins for quite some time, where they use their flood modeling systems. They model the tide, they'll look at the river, the flow levels, they'll look at their flood defense systems, and they'll model the incoming weather conditions and modify accordingly. So they have a good example of a digital twin. The other one is systems that are high value safety critical. So the Rolls-Royce gas turbine example, but also we do quite a lot in the nuclear space for nuclear power stations, etc., for that control and instrumentation. In areas where you want to avoid sort of downtime, cost, or undesirable states, that's sort of traffic systems, for example, or shipping. The fourth one's around where system control or intervention is needed, but can't easily or exhaustively be codified into or onto the physical, i.e. you almost need offline capability to do all of that reasoning and understanding the environment, such that you can integrate that control regime back into the system. The fifth one is where system models are limited and need to be supplemented by that real world data. So a lot of the infrastructure ones are good examples of that, particularly where we are looking at buildings and we're looking at communities, and whether that be the district heating system or aspects such as health and well-being, you actually need to understand it's very difficult to simulate that. So you're combining models with real-world data in order to influence your decision-making. And the final point there is around scale and complexity, where they are such that it's very difficult, almost impossible for human beings to try and comprehend or to understand those in a tractable timescale. So those are almost the scenarios in which a digital twin becomes or potentially offers value. So things like digital health, for example, is an area that's got increasing attention to say what and how might a digital twin of the human body be useful for our health and well-being. So in terms of the workshop, and Ulu and et al., I hope I'm not too far away from the sort of challenge questions that you would like to propose to this workshop. I guess what I see for this community and for this conference and this workshop is questions around what are the compelling applications for a digital twin? What are the requirements for those digital twins in those contexts? Question then becomes, the third question, can a digital twin already be created using current tools and technologies? And in quite a few cases it can. If not, why not? And then what are those barriers and restrictions? And then that will lead into what research is needed to mitigate, remove these barriers or restrictions. And then the final point there of those, the question becomes, what challenges should we, as the engineering design research community, seek to address in the context of digital twins? So I think that brings my talk to a close. I didn't waste time introducing myself particularly, but Professor of Mechanical Engineering, have been for the last 12, 14 years, Head of the Design and Manufacturing Futures Lab at the University of Bristol, and also Head of the Engineering Systems and Design Division here at the university. So thank you very much.
Very much. Thank you, Ben, for that. Very good presentation. And as for the others, we can collect questions in the session chat, or if you start looking into the online Miro board as well. I think we proceed. Eckhard, I think you can introduce our next speaker.
Yeah. Next speaker. Thanks again also, Ben, from my side for that inspirational talk. Next speaker is Bastian Schweiger-Rexig from EM AG, Engineering Methods, giving us a perspective from engineering consultancy on their clients' questions about digital twins. I'm more than curious to listen to your perspective on that topic. Sebastian, the stage is yours.
All right, thank you, Eckhard. I hope you can see my screen. Yeah, looks good. So first of all, hello everybody, and thank you for having me, and also thank you to Professor Hicks for setting the stage in a way, because you already raised some of the questions I want to dig in. So how do you become twin ready from an IT perspective? My name is Sebastian Schweiger-Rexig. I did my PhD at the Technical University of Munich, and now I'm with EM Engineering Methods, engineering IT consultancy. I was told I can show at least one slide. Presenting the company will be very brief. So we are an engineering IT consultancy based in Darmstadt, as Professor Eckhard is. And our customers are mainly in the area of mobility and transportation, but also in many other industry segments. We are about 20 years old, just had our anniversary last week. And yeah, the topic of digital twins, of course, is an important topic for many of our clients as well. So what I was asked beforehand was, what do you think is a digital twin? And I'm quite relieved that nothing that has been said so far really contradicts to this slide. So when we talk about a digital twin, we say that it is a dynamic and cross-domain virtual representation of a physical system that is connected to it for bidirectional data exchange. We already heard that before. And a digital twin is created by the targeted, seamless, and continuous connection of information from different phases of the life cycle of an instance of a product service system. So you see, I already highlighted some aspects that are important from my point of view when talking about digital twins. So first of all, there has to be a physical counterpart. So there is no digital twin without a physical system in place that really exists. And the digital twin shall be somehow cross-domain. So what is important here is that you combine the different engineering domains like mechanics, electronics, software, and all the data engineering as well to form the digital twin. Then we had the distinction between the shadow and the twin already. Thank you for that. So that here we have a bidirectional data exchange or bidirectional information exchange to have the difference to a digital shadow. What is also important here, I think, is that to highlight there are different kinds of digital twins. We already heard that in the presentation of Professor Hicks, so the engineering twin, the production twin, and the operation twin. And from our point of view, the most benefit can be gained if you combine these different twins. So for example, if you get the data from the usage phase into your product development, or if you are able to see how your manufacturing criteria transformed into the behavior of the system in the physical world. So here at the interfaces of different lifecycle phases, the most benefit can be gained. If you talk about a physical system these days, most of the time this will not only be a product, but in most cases it is a product service system. So we are also talking about the digital twin of the whole system, including the mechanics and the electronics and software part. So this has to be taken into account as well. And one of the biggest challenges that we see at our customers is that you need a twin of an instance of a product. So it's not about the type of a product, so that you have a model with aggregated data from all, for example, your vehicles in the field or all your drilling machines, but you need the data of the specific instance that is used so that you can really benefit from the digital twin. So all of these aspects make up the digital twin from our point of view. As I said before, what is important here is to connect the different phases of the life cycle. I guess most of you will be familiar with the V model, but what comes out of the V model basically is only the digital master or the engineering twin, as you might call it. And if you want to make real use of the digital twin, you have to combine the different twins, like the production twin and the operational twin, and ensuring that you have a digital thread that connects all the data that are connected to these different twins. And then once the twin is created, it's not only one twin most of the time, but it's a network of different twins. So to use the full potential, you also have to connect the different products, the different instances of the products in the field to make use of the data they are generating. So now we talked about what can a digital twin be, or how does the network look like, but how do you get there? How do you form a digital twin if you're an engineering company? And therefore, I want to suggest a short procedure model that shows that. So first, we have a lot of customers that try to follow this hype. They have to decide whether it's a hype or it's really worthwhile following it. And therefore, the target definition is very important, and which also includes that you have to analyze your current situation, your processes, your IT landscape, and your business models. That is followed by driving specific use cases to set the scope of the digital twin you want to achieve before you go into the design of the system landscape. And here I want to focus on the landscape that you have in place in order to connect all of these different systems and the data types. Because to implement a twin, there is a lot of housekeeping necessary in the IT landscape of engineering companies. The data that is concerned here lies on different systems that are typically not connected, even in the current status, and maybe on different sides of the company. So you have to deep dive into the current IT landscape to form a future-proof IT landscape here. And for many companies in the engineering sector, it looks like that. So you have your authoring system for the product describing data management, like product data management, product lifecycle management. Then there is all of the simulation data management and the test data management, and the overarching elements like requirements engineering, systems engineering, and production engineering. And of course, if you want to have not only the digital twin type, but also the digital twin of the instance, you also need the manufacturing execution, IoT data, and then some kind of data collection from the use phase, like data lakes and algorithms. So what is the new part here is some kind of a digital twin governance. Many companies think about knowledge graphs to connect all these dots. You have to talk about the interface management and how you integrate partners, because most of the data that you need to build your own twin is not in your possession, but it's part of the partners it's in the organizations of the partners you're working with. So to reach the digital twin in the end, you will need readiness in many areas. So for example, strategic and organizational level, the process landscape and the partner management, and most importantly, from our point of view, in the IT landscape, to really make the twin fly in the end. Thank you very much for your attention, and I'm hoping I can discuss that a little bit further in the discussion sessions following these presentations. Thank you.
Thanks again for that perspective out of the consultancy view on your specific customers. Again, I would like to propose that we postpone any questions to the Q&A session after the last presentation. As the last presenter, I'm honored to introduce to you Mr. Fabian Wilking. Fabian Wilking, he's scientific associate at the chair of product design at Erlangen University. In his academic arena, we all know his boss, Sandro Warzak, and also Benjamin Schleich. who had originally planned to give the presentation, but he had a different meeting, so he had to decline the offer. Fabian, the stage is yours, and we're curious to listen to your presentation.
Thank you very much. Well, just first initial question, you can hear me and you can see the presentation?
Yes.
Perfect. Yeah, I will just start. I mean, we have heard a lot about digital twins so far, so maybe you will hear some of these aspects again in this presentation, because similar as the other ones, we first want to talk about the definition, what in our view is the digital twin. And since you noticed that there are several different attempts to define the digital twin, and it still seems to be kind of like a topic for discussion what the digital twin actually is. In 2020, several professors in Germany have been gathering together and try to fix that problem and make their definition, their kind of like the definition everyone can kind of agree on what a digital twin is. We have heard many of these aspects so far in this workshop already. Basically what is the most important thing is that we always talk only about digital twin if we are having this physical counterpart, which we heard in the presentation just before. So we never talk about a digital twin that doesn't have a physical counterpart, because as you can see on this slide, let me just check to the laser pointer. What you can see on this slide is that the digital twin is kind of depending on the physical twin regarding the operating data. So whenever we get sensor data and we want to process that to kind of fulfill a goal that we set with our digital twin, for example, predictive maintenance or other aspects, we need the physical counterpart. That's something we can't substitute. We need the real data, the process data, the operation data, to process that. And how do we do that? Well, we heard that term already too, the digital master, which is basically, and I hope you allow me that simplification of that phrase, is basically the collection of models that are behind the digital twin. So what are we actually talking about when we talk about digital twins? Well, we kind of talk about the collection of all these aspects. We have the process data, we have the models, we have the IT infrastructure behind it, like how to connect these models, how to connect the process data, and how to bring that or process that into a form where we can give guidance either to the physical twin itself or to a user that uses that information for further processes. And in the next step, I want to talk to you about 2 use cases that we have at our chair at the university. First one is in the beginning of the production phase. We had that before with Christina Wernfjord. And the second one is more about the usage phase or the service phase of the product, where we talk about predictive maintenance operations of the digital twin. But before we go to that, we have been working in a project together with several small, middle-sized enterprises in Germany, and we kind of identified with them do they need a digital twin, and if they need a digital twin, what kind of digital twin do they need? And we have made this attempt to see or identify, can we classify the digital twin? Are there specific parameters that can help us to specify the digital twin, and maybe then, based on that, help these companies to develop the digital twin that they actually need? And we talked to these enterprises, talked about what they want to do, what they want to achieve with their digital twin, and we kind of came to the conclusion that the application level is basically the most important to classify the digital twin. For example, in the first or lowest level of digital twins, we talk about the information digital twin. We want to process data from our system, from our physical product, want to process it and turn it into information that we can, depending on their specific use case, further utilize for our application. Then we talk about the supporting digital twin, which is basically the next step. We transfer the information that we had before into specific behaviors, specific dependencies, and can directly transfer that information into a specific action, like basically for predictive maintenance, it would be something like change part or component because it will be destroyed within a few hours or of usage. And the highest level of the digital twin in our classification would be the autonomous digital twin. So where the digital twin is directly guiding the physical twin towards the optimization of the goal we want to achieve with the digital twin. Of course, this is like a very generic classification, but it helped the companies already to identify what kind of digital twin they need, because as you can guess, like with all these classes, we get several challenges that we have to face. So we introduced some more dimensions. We heard that before, like real-time capability. We need to connect our physical system somehow. One big aspect is also model fidelity. If we want to simulate something, which is main aspect of the digital twin, we have to be aware that we can't simulate every detail, because then it kind of contradicts this real-time capability. We might not be able to act in a manner that we face the problem in time. And then, of course, we talk about the level of integration. It makes a huge difference if we talk about a digital twin for a simple gear, a simple component of a system, or if we talk about a digital twin for a spaceship or like a big complex system. And basically, this classes and dimensions help us to identify components and designs or design activities for the digital twin. So we can more precisely say, okay, this is the digital twin we want to develop, this is the digital twin we want to design, and this is the challenges that we need to face. I want to talk now about the use cases for the digital twin at our chair. The first one you already heard from Christina Wiermifjord, which is for geometrical variations management, so I won't talk that much about it anymore. But what it basically is about is that in production, we equip our production facility and our products with sensor data, so we can simulate their manufacturing process. We can deviate tolerances between that, and with these tolerances, we can directly identify assembly partners for our products. So we kind of skip that step where we need to measure and need to identify kind of by hand like what the perfect partner would be. All in all, the main benefit for that would be increased product quality and of course lower cost, because with the digital twin we skip that one part. All in all, this is part of Smart Assembly 4.0, but I will skip to the next use case that we have at our chair. As I said, it's also difficult, like we talk about the usage of digital twins, but a very important aspect is also the design of digital twins, like how are we doing it? I come from the field of systems engineering, so I feel very safe in using system models, and system models help us to identify their or grasp the complexity of our system. And especially if we talk about complex digital twins, of course, we need to kind of model that complexity. This helps us to communicate with other people who are involved into developing the system. But of course, we were thinking about, well, we have this complexity model, this behavior model. So why don't we use these models? Why don't we further utilize them to actually make them become part of the digital twin, or here in this case, the digital master? So what we can do is we can define the behavior. We can directly utilize it to an executable code for our digital twin. And we can set specific scripts, so we can start simulations, we can run machine learning out of it. And that's, as we heard before, a very interesting aspect of the digital twin. We don't only have the simulations we can run, where we get precise information about our digital twin or our physical twin through the digital twin, but we can also integrate aspects like machine learning. So we can combine these aspects, like fast, quick machine learning aspects, with maybe detailed simulations, and then see, okay, what would be the benefit of combining this. So what is the main benefit of utilizing system models for the digital twin? Well, we get the good parts of the system awareness. for using these system models, and we can directly use them for or utilize them for our digital twin to actually construct our digital twin, and for example, in this case, achieve something like predictive maintenance, where we combine the simulations and the machine learning part. That's basically it about our use cases at the chair. We came up with also with 3 questions for future challenges. First one is like, how do we overcome the complexity and interdependencies between sensor data? I introduced that a little bit before with the system modeling, but I guess that's way more discussion we can have about this. Then one aspect that we never really talk about in engineering, but that is really, really important as we have been talking to specific enterprises now, is like, how do we consider legal aspects? Everyone wants to create a digital twin, but for example, if we create a digital twin for a component that becomes part of a bigger system for the OEM, how are we considering legal aspects there, like their data exchange? Maybe that's a particular German problem, but I think that's something we definitely have to talk about. And then regarding the design society, we heard that challenge before, but I think it's very important. Are we ever actually having sufficient approaches to design digital twins, or do we need to adapt our current approaches to face the challenge of digital twins? And as we have seen in this presentation, the different classes and dimensions of digital twins. And with this, I'm done, hopefully in time.
Fabian, thanks for that very, very detailed presentation with the 2 use cases. I think this was the closure of the session of those inspirational talks. Thanks to all the presenters. And I would like to open the discussion. We have round about half an hour. We're just right on time. Start the discussion of the presentations. I do not want to start myself. Who wants to ask the first question to the presenters? Don't be shy. Okay, if there is no question from the auditory, I may be forced to start myself. I would just like to ask the first question yet to Fabian. You mentioned on one of the last slides that your digital twin can be used for condition monitoring purposes. With the second concept, my question is, how does the digital twin know how to age in the same way as the physical twin does? What is needed in terms of sensors, signal transfer, etc., for that concept in order to work?
I think that's one of their. Can you hear myself?
Yeah, you can be understood.
Yeah, what I wanted to say is that this problem is basically very individual. Like whenever we talk about a digital twin, we always try to imagine this one generic concept of a digital twin, but basically in the same manner like the physical products vary from each other. Like a car is completely different to a simple gear or to a space station. We have to be aware that digital twins also vary in their IT infrastructure, the sensors, and of course mainly in the models, which are kind of the core element. So that's something you always have to consider, how to adapt your system to face these challenges of the aging process. But I guess that's something like you really have to answer individually for every single product, like how to face the challenge that my physical product is changing by time, which I have to then kind of integrate into my models, because my models basically in the beginning only represent the initial state of my physical product. So maybe we need to adapt these models. Maybe we can integrate this aging process into the models. I guess that's a very individual problem for every physical product.
Okay, thank you. Any other questions from the group?
I think we have some questions in the chat.
We have some questions in the chat as well. Perhaps we should follow those a little bit and keep these discussions concise but clear. But since we will have the workshop coming up as well, where we will interact. I think Stefan Hausig, you had a question before. Do you want to repeat that in public?
Yes, I can repeat it. I think, but I think already Ben gave a very good answer to this afterwards. My question was for the first presentation, which types of digital twin you use at SEV? Because my impression was you spoke more or less about something like a digital master, which was discussed also in the other presentations, because when you want to support the design, then you don't have a physical twin at this time. This was my impression. So my question was which types of digital twin you spoke about during the presentation, but I also have the feeling, like Ben said, that the digital twin only can exist if you have a physical twin existing besides this one.
Yeah, feel free if you want to comment on that, or if you should go on.
Nice. Just looking to the chat.
He may have left actually, so I think we can bring it up. The role of support systems in digital twins is probably quite relevant. Sayema, you had a question as well for Ben and others.
Yes, I think Ben's answered it in the chat, but I think one thing we're hearing from companies that the zeros fall off the bill when they look for investments in digital twins. And I'm wondering what is the criteria? What would we be looking at as a benefit of digital twins over, like Ben talked about, all the other areas that are already in the research areas and other types of models?
Who wants to?
So actually, if I should, perhaps you can ask, I don't know if Freddie is still with us here from Volvo.
Oh yes, most definitely.
Do you have some, what's your expected benefits or the cost benefit perspective from a company such as Volvo on digital twins?
I will try to keep it short, but it will be hard, okay? To begin with, I would actually say that, in my opinion, based on how we have been conducting research in the past, there is a predecessor to the digital twin working in the early phases, because that's where we really are leveraging on utilizing only geometry. So I mean, in one sense, that is really what is eventually becoming the digital twin. But aside from that, when it comes to the business benefits and everything, we are currently in these very discussions as we speak, and has been for quite some time now. Because one of the large areas where we see that we will benefit from the digital twin is actually in the downstream processes, such as manufacturing and also aftermarket in the product life cycle. When we want to conduct service on our products over a long period of time, and the product will change over time, and you want to really understand, and I will not utilize the naming instance, I will utilize the name individual, because individual is each and every truck is an individual. So that's where you can bring a lot of value, but the challenge is really how to keep the digital twin up to date continuously over that product life cycle, because that requires skills and modeling understanding that is not necessarily something that the aftermarket area contains right now.
May I also comment on that question about, when does it make sense to create a digital twin? I just grabbed a teaching exhibition model from my other desk here. one of the SEW products, and it's a small transmission motor, and it's not too heavy in order for me to lift it up on my desk here. So I think this is a product where it definitely doesn't make sense to provide it with a digital twin, because it's not such an asset that it cannot be replaced within a few hours, and that the cost for a replacement part is manageable. I think it's different for products which really have a high value when it comes to delivery time for spare parts, with a huge financial or economic consequences of a product failure. I think this is where the digital twin can pay off itself very quickly. And I think that's also the question is, if we want to look to the digital twin of such a transmission or drive technology, do we really need to represent all the components, or just the critical ones, as Fabian mentioned? I think I'm a machine elements researcher by heart, but I have to confess that nobody really cares for a rolling bearing or a spur gear. People care for the well-being of a machinery, that it's keeping up its productivity. And I think this is the thing that we need to keep in mind when talking about the digital twin. We just have to deliver the information that is required from the digital twin, not overdo and make it as complex as research wants it to be. It needs to be as complex as it needs to be in order to fulfill the requirements.
Sorry.
I think this is the question we have to answer.
So I mean, Simon's question is excellent, and just to put a spanner in the works for you, Eckhard, is that we had a program of work that was looking at digital twins of electric machines. In particular, it was for an oil and mining company, because all their conveyors are, once a conveyor fails, it's a single point of failure, they stop producing. So we spent £300,000 on instrumenting a conveyor, and we applied very detailed models to that to look at condition, to understand and try and type modes of failure and what the precursors were to those modes of failure. To cut a very long story short, we ended up by using features in the MPEC, motor power electric current signal, and we found for £15 current clamp, we got exactly the same reasoning. We could draw the same insight with the same confidence as if we had £500,000 worth of sensors looking at acoustic emissions, etc. So in that case, the digital twins of their conveyors were effectively looking at the motor power electric current signal during startup and operation. And we were able to look at the different frequency ranges. We could say that's an issue with the bearings, that's a gearbox issue, etc. And you could start to type. We have a program with GKN, which was my response to Simon. It's exactly the challenge they have. It all looks wonderful, and people tell them, yes, you can have the world is your oyster. We can use NVIDIA's Omniverse, and you can have a digital twin of your whole factory and extended supply chain. But what is the cost benefit? And I think this is where it's about the purpose of the digital twin. In the electric machine example I gave you, the solution was simple in terms of technology. The challenge was in terms of the research challenges were in terms of what techniques you use to be able to identify the features in the signals. We did quite a bit of work, just changing it totally, quite a bit of work at the city level. And we did a lot in Bristol looking at the whole city. And the challenge for us there is we have a digital twin of a very famous bridge in the city, but nobody wants to pay for that digital twin. And when you look at the city level, there's this bystander syndrome. Nobody wants to pay. In an engineering company, they'll cover the cost, but it's cost benefit. When you move to larger systems like city systems, that value stream, who owns what data and where that sits, is a real challenge, and very, very difficult to resolve.
Okay, should we see? We actually have one more question in the chat as well, or do you want to Anyone else who want to comment on the last thread here?
I would like actually just to add on to what Ben just said, because I mean that's one of the true challenges. I mentioned storage solutions in my presentation, and I mean this is really a true challenge going forward, because if we are manufacturing a couple of 100,000 trucks a year, and they last for say 10 years each, and they should be maintained over that time in order to be consistent. And then we are not talking about having a 100% in-depth accuracy on those, because routing and stuff like that is tremendously hard to solve. That's a huge cost, just administrating those digital twins, and it's a hard time finding the business value of having all those up in the air at the same time. So there are challenges going forward with digital twins. I mean, it's definitely a huge potential, but there are trade-offs that needs to be identified in order to find a sweet spot.
Just one comment from my side also to Ben. I agree with you. We need to find out the right way to predict, especially failure, or to detect failure. But in many cases, that's at least my impression. We have concepts to detect a failure when it's too late. So if we can provide a hint for an upcoming failure, it's probably changing the attitude of people who should pay for the digital twin. So we have to chew on that to provide a solution for the future. Just a comment.
Yeah, and that was my point around the absolutely. It's a requirements capture process you've got to go through with a digital twin, and we certainly had with a company that make large wind turbines. They are preoccupied with typing, what we call typing failure. So actually, can you isolate it in the transmission or the system? When you actually don't, what they want to do is know that what are the precursors to failure, how much remaining useful life might there be, and do they prioritize swapping out the gearbox? That's a different question to actually, can we identify spalling in the bearings in the gearbox? And please don't quote me on this, but they take us into this massive, hugely detailed digital twin that's high fidelity, when they actually, in terms of commercially, they don't want that. They just want to say, minimize swapping out the gearbox. It's about €1 million, something like that, per gearbox to swap out. The whole cost of that. So that they don't want to swap them out. So they want how much remaining useful life, and when they take the gearbox out, they can do their forensic engineering.
I can also comment on, since we are discussing this, I think that when we talked about criteria, I think there's a business criteria as well. When you as a manufacturer have the responsibility or the cost of any kind of a failure of a product or something like that in production or in service, I think, and you can mitigate that or avoid that by any kind of digital twin solution, then it starts getting interesting. But as long as we have a produce to sell and you make money of failed products, then I think the rationale is not evident for the manufacturer. So it's in that way it's connected to the business model. That's one observation. There are actually, I don't know, now we'll come down to comment. Should we continue with the last question? I don't know, Stefan has a comment or John has a comment as well. Is there something you want to bring up on that? John first, or?
Maybe I can give some further information for my comment. It's always very interesting during product development when you think about which digital twin use cases we want to support. This means especially what we already have to add to the normally real twin, this is especially the hardware part, and which can be added afterwards, for example, if you update some software, something like this. I think this is also a very interesting topic, Eckhard, and we discuss together. I don't know if you have any experience, how to consider the most relevant use cases already during the initial product development, or do we need something like a modular architecture to add some sensor actor elements afterwards? Does any one of you have some experiences in this field? Because currently we have to add a lot of sensors, a lot of actors to the physical twin, and I think this is not the most efficient way, because then the product is very expensive, maybe also very sensitive to some disturbances and so on. And we have to find a good way how to make the product smart as possible, but also to support the relevant use cases afterwards.
I think the key solution element will be in many cases what we call soft sensors, as Ben pointed out. As soon as we are able to monitor current draw, voltage fed into the driving motors, that can give us at least a hint on what is happening inside a driveline. But it will very soon become more difficult as long as we probably have a hydraulic circuit where we can't see anything from the current draw from the electric motor. Probably it's even combustion operated. So we need to think about how to find those sweet spots, soft sensors, probably usable, sensory utilizable element effects along the process chain.
Yeah.
So
I think it's one part of the puzzle, but I think also, like Ben said, we also have to discuss, do we need actors or do we something lead? Because we also want, as in many cases, modify the physical twin. And I think then we also have to think about the actors in the system.
And Nate, again, just for avoidance of doubt, I think in many cases, people get fixated on physical measuring or sensing of a particular attribute. And where I was going with the motor example is we demonstrated that you can infer the onset of failure with as much confidence if you measure motor power electric current as you can if you try and measure acoustic emissions or actually have a sensor there that's measuring the clearances, for example. And so I think, again, it's back to with the digital twin, and this is a cost benefit. What are the insights? What's the purpose of the twin? What reasoning or inferencing capability do we want from that twin? And that will then tell you whether you can start to look at whether the models that were created during product development can be manipulated and modified in some way to provide foundations for that, or maybe not. Actually, there might be something that you can do that's a much more simplified model that gives you that same inferencing power. And that program of work really demonstrated that you don't need to go down this high definition geometric route.
Of course.
With acoustic emissions, we could get it really does. It's that purpose of the digital twin that's absolute key. And as engineers, what are the requirements that we want from our digital twin, which relates back to Simon's question of it's got to come from the business case. And if you had that inferencing capability, what would you do with it? And what does it mean from a bottom line? What does it mean for the trucks, for Freddie? What does it mean for customers? Where's the value in doing that?
Yeah.
Just a brief comment on that particular one, because I made some notes in the early presentations here, because when I started to perform my research back in the end of the 90s, we were really targeting to pushing forward the introduction of the physical prototypes. That was in what we were driving inside the CAD environment in order to optimize how we model and create the start for the digital twin, but also in a lot of other areas concerning simulation, finite element models, and so forth. And I mean, this is really where we see a lot of gain today, is that we don't want to introduce the physical twin until we have reached a certain level of maturity on the digital representation of the product. And of course, we will never be able to take it all the way without introducing the physical twin in order to validate our assumptions and so forth. But that's how we are really targeting today, is to take as much as possible up front without introducing any type of physical twin. And the reason for that is that we have so much information on our existing products that we can make comparison against, but even though they are not exact digital twins, by engineering judgment, we can make fairly good assumptions on how we can make and utilize those models for prediction.
So what you actually are raising is the time scale of iteration of connectingness in some sense.
Yes, correct.
We have, I don't know, we are getting close to a phase where we should go into the workshop and be interactive. We have an introduction to that session as well, I believe, Yannick. So
yes. So we'd like to invite you to go to the My Report. I've just sent the link into the chat. I will also share my screen that you will see where are we and what are we doing. Just
we had also, so I think you can show that first, and then yes. I guess we all need a few minutes of leg stretch before we dive in there.
Yes, exactly. Yeah, now we are here at the workshop stage. First, we'd like to get some visiting cards from you. There are already some where we can walk on later on, or that we can use them and get to know you. And in the second stage, you can unlock the group work session. We have 5 different groups, and we also prepared the questions, which we will put on top of every group work. We divide it in 3 stages. So first we look at the question, look at the boundary conditions which are important for the question, and then we can talk about how can this question be further described, that everyone of the group has the same understanding. In the second phase, we go to the discussion on the question. So we want to know what are different points which are, especially for these questions, relevant to further describe and answer this question. And during this, we also want to get the outcome maybe into 2 or 3 sticky notes or points which are especially important, and so everybody in the group can be aligned with these outcome and have the same understanding at the end. And we would also like to ask you that you protocol all of your outcomes or of your ideas in these group work session, so that we can later collect all the ideas and then nothing is lost. And for the usage of the My Report, we have this toolbar on the left side. Mostly you can work with these sticky notes. This is just a note. You can choose the color and then also the size and put some text inside it. And furthermore, if you need some further shapes, you can also use them to group and get your ideas onto the board. And you can also connect these by the dots at each of the fields to the text fields. So you can also get a little bit more structure into your ideas. And that's it. Now we will set up the groups. We have some predefined questions and also the breakout sessions where we will work in the groups. We'll send it into the chat, and also we have set up the group sessions. So you can now get a little bit familiar with the My Report, maybe also answer some questions on the left side onto the digital twin. And then we will maybe start at 15 o'clock with all the group discussions and get into the groups. I think also Sebastian and Fabian want to be an expert or moderate one of the groups. We took also some of your questions. I don't know if you, Ben Hicks, also want to. We have also one of your questions, and that will be something we can talk about now. Are there any questions according to the group work?
We should repeat the start time as well and things, and when we finish and reconnect in the end.
Yes, so we will start at 50, maybe 5-minute break now. So 2 past 15, and then we work 45 minutes in the group, report our outcome, and at the end we will have a wrap up.
And we have random distribution of the participants to the groups.
Yeah. And we can also say that in the end, when we gather, we will also mention how we intend to proceed from this workshop to make it not just a standalone event.
Good. Then let's have a 5 minutes break. 5 minutes. If I look to the watch on my PC, it's 14:58. Shouldn't we start at 15:05, which is a realistic 5-minute break, which allows everybody to, I don't know, do the logistics in order to enable us all to follow the discussion in a meaningful way. Okay. See you soon.
Finished. Robert, I don't see any possibility to get the participants back or to close the breakout rooms. Is there one?
I just left and I got back to that main room.
Yeah.
Let me just check.
You can leave, but I don't think that I, as a moderator, can stop all the breakout sessions.
I think the breakout sessions ended automatically.
Oh, they ended automatically. Okay, fine.
At least
because I was just wondering where all the people are, but maybe they will come now step by step.
Yeah, all should be here.
Okay, perfect. So, yeah, it was a little bit confusing at the beginning. Sorry for that, but I saw that we have had a lot of sticky notes and I think also a good discussion, at least what I've saw or heard. And yeah, maybe now we can go back to a small wrap up of all the groups. We don't have that much time as firstly planned, but maybe I would ask the first group to directly start, give maybe a short, maybe 1 or 2 minutes, small introduction to their discussion and especially at the outcome of the end. So I don't know who was in group 1 as I renamed them, and we had 2 groups which has the same name, but if there's anyone from group 1, I think can directly start to give a short introduction to their discussion. I will share my screen so everybody sees the Miro board.
All right, I think group number 1 would then be us, as it had my name there, and we talked about the toughest challenges when making a company or its IT landscape twin ready. Maybe you can zoom in a little bit on the Mentimeter slide. So we started with a short survey among the participants. So where do you think where are the highest challenges concerning methods, for example, a use case catalog, tools, processes, data management, people and culture, business cases, or something else? Under the domain of something else, we had the lack of a definition and expectations, as well as legal issues. And then we went a little bit deeper into all of these domains. You can see it by the notes underneath in these 5 categories. And just gathered, maybe you zoom out a little bit, we gathered aspects or examples what are challenges in these domains. We didn't go as far as to look for solutions for them, as we do not have the time for that, but at least gathered some challenges here. That's something that can be investigated further in the following. And then maybe we just directly, shall I go to group number 3, because I think this one was empty, and we just took the space on the Miro board as we did not have so much.
Yeah, so then you took both, fine.
Yeah. So this was the second part then of our group discussion. Who should be in charge to make the twin fly? And again, if you zoom in on the Mentimeter, there were the options of it is the R&D, it is the engineering IT, somebody else, or some, as I called it, some dedicated twin setup team. And as you see here, this is the option that got the most votes, and number 3 can somehow be integrated after a short discussion there, I guess, too. So then we took the rest of the time to discuss who should be part of such a twin setup team. And basically, we listed down a lot of domains that should be represented in there, but did not have the time to go into detail how you could manage to set up such a team, because at least from the companies we are working with, this is how some companies try to do that, to form these teams. But again, if you want to include all of the domains, you get pretty large teams, and that cannot be used full time in these teams. While on the other hand, at least in our discussion, we agreed that this has to be some dedicated team that is outside of the line production. So this is still something that can be investigated further. Who should be ideally part of a twin setup team, and how do you incorporate that in your organizational structure? Questions or comments on that?
Thank you for the interesting explanation, and also a lot of work you have done in the time. Thank you. Are there any questions?
No, not a question, just a comment. I think we were working on the same working space by bad coincidence. It was.
Yeah. I was realizing that there's some notes were popping up all the time.
Among them, Freddy, and we were six in that group. We were also discussing and putting sticky notes on the same area. Just one comment, one addition, because then we have done also our group. The idea was, or the statement was, we need to have a good understanding of how to establish that data connection between the real twin, physical twin, and the virtual twin, to be able to manage that data exchange. We have to understand what data is important, what is irrelevant, and we were also discussing the input of Freddy that in many cases it's not really state of the art to have a real digital twin. We have something like a physical bomb. What is inside the car? What is inside the product? But we don't know what the fingerprint of the components is, so to say. So we're falling short in many areas, simply by the reason that we don't have sufficient data, that we don't know how to manage the data flow in a decent way without causing too much inefficiency and energy waste. Was that our discussion? Just seeing Freddy here being present in the auditory.
Yes, I'm here.
Anything to be added?
No, I'm just saying that, I mean, it's a true challenge taking the digital twin to the heights that we really would like it to be for particular products. There are products where it's motivated and realizable to reach 100%, but for other areas it's much more tougher because we have so many different. We were talking about instances before. I would call it individuals.
Mm-hmm.
Yeah, and that's the challenge. how do we keep all the individuals then up to date?
Good.
Perfect. So
much sorry for messing up your agenda,
no,
Yannick.
it's fine. It was good. It was perfectly right. We worked on the same team or theme. So maybe the second group can talk a little bit about their.
Yes, I think I will just start with that then. It was very interesting discussion. We had this very generic question of whether existing design approaches for the digital twin are sufficient enough, or do we need like new ones? Do we need a bigger framework about it? And we were basically on the Mirrorboard collecting aspects that come with it. What is the state of the art? What else do we need to consider? And we came to the conclusion that this question in industrial context needs to be separated or cleaned by the fact that many enterprises that struggle with implementing digital twins are maybe not suffering from an maybe not existing design approach for it, but it's maybe more like a competency problem. We have lots of maybe very mechanical oriented enterprises that now want to implement a digital twin, and then they need a whole new aspects to consider where they didn't have the competencies in beforehand. So we tried to clean that from that. The question whether we need an approach from the aspect whether it might be a competency problem. The next aspect was for all the single elements of digital twins, we have individual approaches to focus it. We have for mechanical problems, for mechanical products, we have that for electrical products, for information technology. So we were thinking about, okay, is a digital twin maybe just the sum of these individual approaches? Do we just need to like follow them and then combine them in the end? Which we all agreed on, well, maybe no, that's not the case, because we want to have an optimum in the end out of it. And then in addition, we have loads of other aspects we need to consider. We have legal aspects along the whole value chain till the customer. We have scaling problems. I mean, we have seen lots of examples of digital twins that might work in their individual scenario, but if we want to scale it, if we want to send out like millions of products that kind of are digital, that have a digital twin, we need to think completely differently in, for example, model management aspects or data management aspects. And of course, what is also very important is that a digital twin is always very, very much associated with the business model, because in the end we have to ask ourselves, why are we creating a digital twin? Because we want to sell something, we want to sell it as a service, for example. And therefore we came to the conclusion that we already have very sufficient approaches, but what the digital twin might need to cover all these different, also not non-technical aspects, maybe we need kind of like a framework around it that covers these aspects and tries to grasp their interdependencies that exist between these different aspects that we need to design digital twins. And that basically is the outcome of group 2 to that question.
Thank you, Fabian. Are there any questions? So then, thanks. Then we directly go to group 4. I think, Martin, you wanted to wrap it up.
Yes. So I think we observed this topic a little bit from a little broader context than this very industrial application, since none of our group was, or I think I was the only one who worked on a specific use case. So basically, we first thought about what are the applications of a digital twin. And I'm working on human digital twins in healthcare. which is a pretty different application from what we've heard so far today. And yeah, we thought about that it could be categorized as you can have product digital twins that are tied to a specific product. You could have process digital twins that could be tied to a specific process. And you can have system digital twins that are more on a higher abstraction level. So there was the question in which abstraction levels or what is called integration levels, basically, digital twins could be. And based on that, we then posed the question on what is the definition of a digital twin for each of those. And I think where we agreed on was also what was mentioned in the presentations before, that there needs to be a physical entity that is the key requirement for digital twin. And there needs to be a data connection. And there's a question on how or what does continuous in that context, for example, mean? And how does this data connection look like? For example, with a human digital twin, you cannot measure the human continuously in terms of permanently, but you can measure him continuously in terms of regular appointments with a doctor or regular sessions. And I think in the specific use cases, those would be enough. So I think continuously does not need to be permanently, but there needs to be a somewhat a synchronization at some point to the physical entity. Then there was a question on how do you categorize digital twins, also in terms of like the specific application fields. And yeah, we came up with that maybe the digital twin itself does not need so much elaboration on the general definition, because yeah, we already heard today that there is a consensus on that. But I think that there are many, many new applications, and they need adaptations of those conventional, of those general definition regarding to that specific use case without contradicting the conventional definition. Yeah, I think that was basically what we discussed.
Thank you, Martin. Are here any questions? If not, we would go to the last group. There are also some sticky notes. Who wants to talk about this?
I think, Yannick, I think I'm the only one left. Simon had to reach. I'm conscious of time, so I will be really very swift with this. And we've talked about just enough definitions in that last, was it Martin talked a bit about that. At the start of this, we shared our thoughts on it, and our conclusion was stop creating new definitions, use the NASA definitions from 2002, 2003, unless they're deficient. So people have to demonstrate they're deficient if they're going to adopt some new definitions. We talked again about it being very unhelpful. There's a lot of conceptual stretching and conflation, which I mentioned in my talk. But our view is that both industry and academia are culpable here, because we will, when we bid for money, we will conceptually stretch digital twins in order to secure our research funding. And then there was a question here raised by one of the group around in engineering design research, are we reinventing the wheel and going back over and over and over definitions when other fields are relatively mature and we just need to accept their definitions and move on? With that in mind, we fixed it and we moved on. We looked at, in particular, the opportunities and the challenges, and we felt that the real opportunities lie in ultimately improving simulation approaches. So now you're modeling the digital twin, you can start to ask the questions, why are your predictive models not as accurate as they could be? The second one was around, business case being, and key requirements, and the opportunity is, what are the techniques to undertake or perform requirements capture for digital twins? And that relates back to, I think, one of the other sessions when they were talking about what are the skills. And I think the blue post-it note, I think it was board 2, was us saying, our conclusion from that was, is there, in order to design, to capture requirements and to design and develop a digital twin, is it a combination of systems thinking combined with design thinking combined with sort of model-based systems engineering? We taught this link to Freddie's talk really about, there's clearly an opportunity with long life products or artifacts where you can learn across the generation to improve your current products. So that feedback from the digital twin may feed into the current products, but also you can learn at an aggregate level from all those digital twins. Lots of opportunities we're seeing in terms of what they call synthetic populations. So actually a digital twin of a particular city, for example, you actually use that to generate a synthetic population that can then be transferred to other cities. There was some talk around an opportunity for sharing across supply chains. So actually, if you had your digital twin of your component, could you share it or even generate some revenue by giving that digital twin to the OEM so they can actually do a whole system simulation? Moving on then to challenges, the cost benefit challenge really is what are the limitations? Is cost benefit, the what we call pursuit of perfection. When ultimately we said, if you speak to someone in sort of flight physics at Airbus or Boeing, they will want their mindset, they're pre-programmed to think about very detailed CFD models with flow separation, etc. Actually, for the purpose of the twin, such perfection or high fidelity may not be needed. The limitations is just always been the same with virtual prototype versus prototyping versus physical prototyping, is when it's actually quicker to do it practically, and there are cases of that. One of the challenges, sort of penultimate one, is around who owns a twin, who's responsible for it, and who pays for it. Particularly again in long life products or products or systems. And then the final point, there are lack of standards around digital twins and specification thereof, particularly within the different fields or different disciplines, which again, I know Martin and a few others touched on as well. So thank you.
Yeah, thank you for the final wrap up. I think there was a lot of interesting discussions and also a lot of outcome. If there are any questions regarding the presented results, we can get over to the last point. It's the networking. Maybe Eckhard or Ola, you want to say something about it? What you can do, we have three. What you can do is you can get your visiting cards, and get it to the slide or to the board you want to participate.
I think one of our key ideas for that workshop was to identify potential contacts in industry and in academia with an interest in designing digital twins. We thought about potentially this could end up in a second symposium or in some kind of a joint paper, which is relevant not only for the industrial, for the academic participants, but which may also prove to be beneficial for industry representatives in order to gain insight in what we are doing inside academia. So that was basically the ideas. Oscar, do you want to add anything when you've missed out important facts that we discussed previously?
No, I think the general intent is for us to build on this excellent session, and to, in my view, it would be really nice to have a conference around digital twins. I think it's important enough, and if not, at least a roundtable and a publication. Try to keep the momentum going. I think it's an important topic, and I'm quite novice at this, and I found this session to be extremely informative.
I think it's an academic question to find out what is the appropriate journal to address such a paper. Potentially, we can get an invite for the Journal of Design Science to present some kind of an overview paper, which could be a collection of the input from this discussion. This is one way. If there is any more reasonable approaches, I would be happy to hear about those. Otherwise, we would wrap up in a short meeting afterwards with the organizers, and then contact the contributors, the discussion participants afterwards, and ask for willingness to contribute in such a publication, and potentially also discuss with the board whether they see a chance to really squeeze it into the design science journal. Okay, I think Ula had to leave, or I don't see him anymore. So I'd guess that he had to leave. He mentioned something that he has a
Ule is here.
Okay, you're in the same room?
Yes.
Okay. Just I wasn't able to see him.
Can you hear me?
Yeah.
Can you hear me? Can you hear me?
Yeah.
Hello?
Yeah. Prata.
Hello? Can you hear me? Can you hear me?
I think we can hear you, Massimi.
But we can hear you.
Yeah, okay, I'm here. Can you hear me? Okay, so the thank you very much. It's been quite exciting as we heard. We discussed it in the design practice special interest group. We said that we wanted to have something which is highly relevant industrially, but also of great interest academically. As Ben and others pointed out, there has been quite a lot of work done already, but there is still this area we seek best practice and which is evolving based on expectations. Of course, we will discuss this further.
Massimo, you are on mute.
Relevant.
Again.
So now it should work.
So we try again. I think this is an area where we have good progress made already since 20 years, as Ben pointed out, on digital twins, what it is. We see also that there is a big movement industrially to make benefits of digital twins. So a potential way forward would be to discuss the effectiveness and implementation. We try again. Third time. We said that the implementation and change and adoption of the digital twins in industry. I think that's an area where we benefit both academically and practically to extend the discussion. I think what we can do from the design practice is to invite all the participants from this one from a follow-up activity where we can discuss that topic. It could, of course, be a paper on that, or there may be room for other adventures as well. I think that's been very good input, both from all speakers and all participants. Thank you also very much for the moderators and facilitators in the session. So I think we have to digest that, and as said, we will have a short wrap up in the organizing team, and we will definitely follow up with you who have attended and those who have already left, and invite you for any kind of after work.
Okay. Yeah, then if there is no more comments from other participants, I'd like to conclude that workshop session. Thanks to every participant for the good and focused discussion. And yeah, we will invite you to participate in a joint publication as soon as we have digested the outcome, had a chance to look at it, how to reuse that material in order to gain benefit for academia and industry in the end. Thank you.
And just to say, thank you, if I can, on behalf of all of us, Oscar's clapping his hands, Eckhard and Ola, etc. Thank you very much for taking the initiative and organising this session and all the planning work, etc. by everyone. Thank you.
And also to Yannick, he did most of the legwork. I wasn't doing it myself. Hands to him.
Yeah, thank you, Yannick.
Thank you all for the participation and nice discussion. It was very interesting.
And take care, everybody.
Goodbye.
Bye.
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 Bye-bye.